Hey guys, this is Avery Morgan. I'm doing the test one video bonus points covering chapter 12, which include questions 13, 20, 42, and 79. If you have any questions or need further clarification about anything I say in this video, please feel free to reply to the post I make in Teams with a link to this video. I'll do my best to answer it if I know the answer. However, please keep in mind we're in the same boat here, so if I don't know. And let's pray to the gods that Professor Brian also sees your question. So, with that out of the way, let's go ahead and start with question number 13. For the reaction given, the observed rate law is that which of the changes listed below would affect the value of the rate constant K? So, since we are looking at the rate constant K, specifically the value of, we need to look at a very important equation. This equation is the Arrhenius equation. If you're not sure exactly what this equation is, it's on page 22 on our chapter 12 notes that Professor Ryan has provided us with. And the equation looks like this. It is K is equal to AE to the power of negative E sub A R times T. And for everybody who doesn't know exactly what this equation is saying, let me break it down a little further. A is the variable for frequency factor, here we go. E is just the number, it is not a variable. E sub A is the energy activation. R, of course, is our gas law. And T is for temperature. So to properly analyze our answer choices, we need to make sure that they include one of the components in our equation because all of these components affect the value of K. So if what the answer choice is talking about if it's not in our equation, then it is incorrect because it won't affect the value of K. With that in mind, let's go ahead and look at option A, increasing the partial pressure of oxygen gas. This does two things. One, of course, increase the pressure. And then two, it also increases the concentration of O2. Concentration and pressure are, neither of those things are in the Arrhenius, Arrhenius equation. So therefore, changing the pressure or the concentration won't affect the value of K. So A is incorrect. So now let's go on to B, changing the temperature. If we change the temperature, how does that affect K? Well, we see that temperature is one of the components of our equation. So if we change the value T, we are also changing the value of K. So B will affect the value of K. Now for C. Using an appropriate catalyst. To really make sure we understand this one, we need to know what a catalyst does to a reaction. A catalyst lowers the energy activation of a reaction. So, since energy activation is definitely one of our components in the equation, by lowering the energy activation, we are changing the value of K. So C is also one of our answer choices, one of the correct answer choices. Now for number 20, ignore my previous attempt of this recording. We're going to restart. So, considering the following energy plots for the chemical reaction, when answering the questions below, we're given a graph. Which plot, purple or blue, is the catalyzed pathway? How do you know? So, like I just said before, a catalyst lowers the energy required for a reaction to occur. And on a graph, that is illustrated at or shown at the top of that graph or of the line, and that is called the transition step. So by lowering the amount of energy required for the transition or for the activation of the reaction, that's how we know which one is the catalyst. So the one with less energy is going to be our catalyzed pathway, and the one with more energy is going to be our uncatalyzed pathway. So as we can see here, blue definitely uses less energy than the purple pathway. So we know it's blue. And I'm not going to write everything out because I'm going to be explaining it to y'all verbally. Our answer is blue because it has a lower energy activation. I'm just writing the variable for that, which is what a catalyst does to reactions. And I've abbreviated some words there. So now let's go move on to B. What does delta E1 represent? So let's look at what delta E1 is on the graph. It is a line ranging from the top of the purple line all the way down to where the reactants are. So since it is the range or the y-axis, which is our energy, and since it's described with the uppercase letter E, we know it's talking about energy. So, and since the line also goes from reactants to the top or to the transition step of the purple line, we can conclude that delta E1 represents the amount of energy required for the reaction to occur without a catalyst. Now, for C, what does E2 represent? We're going to look, I need another color, we'll use purple. From here to here, this is E2, we're working with energy because of what the y-axis is and the fact that it's marked with uppercase letter E. Now we need to look at where that line is pointing from. It is going from reactants to products. So delta E2 is that showing us the energy, the change of energy from reactants to products. So change in energy, again, the change of energy from reactants to products. Now, for the final question, is the reaction endothermic or exothermic? Well, to answer this one, we need to look at what we wrote down for C, or we need to look at the line for delta E2. We see that reactants only take this much energy, whatever that number may be, and products have this much, they have this much energy. So we know that since product is higher up on the line or up on the y-axis, we know that products have more energy than reactants. Since the products have more energy, that means during the reaction, energy was taken in. So our reaction is endothermic because because products have more energy than reactants, meaning that heat went into the reaction. And I trust you can write that down because I don't feel like spelling it out. 42. A certain reaction has the following general form. Coefficient A reacts and creates coefficient B. At particular temperature, the concentration of the initial concentration of A is equal to 2.8 times 3 to the power negative times 10 to the power of negative 3 molarity. Concentration versus time data were collected for this reaction, and a plot of 1 over A concentration of A versus time resulted in a straight line with a slope value of 3.6 times 10 to the power of negative 2 liters per moles per second. So that was a lot of words. What are they asking us? A, determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. So to answer A, we need to derive a little bit more information from the word problem. Since this reaction has a plot of 1 over A, we know that tells us that the order is the second order. So we know we're working in second order. Well, let me backtrack just a tad. For the rate law, we know immediately is R is equal to K times A to M. We know what M is in this case because it tells us the plot is 1 over A, which tells us that it is the second order. Therefore, M will equal 2. So the rate law now looks like this. So boom, that's one of them. Now let's do the integrated rate law. The integrated rate law looks like for the second order looks like this. It is 1 over A sub t. It's equal to K t plus 1 over A sub O. So K being our rate constant, T is time, A is the initial concentration, and then A sub T is the concentration after after a given time. So there we have it. That is the integrated rate law for this equation because again, we were told that it is the second order here. And I am just making a mess of things. So now, how do we find the value of K? What is the value of the rate constant? Well, in in the word problem, we are given the slope of the value of slope of the slope of the straight line, which is super important because all these r- integrated rate law equations, no matter what order it's for, it is a more complex version of y equals mx plus b. So 1 over at is y, k is m, x is t is x, and 1 over ao is b. So if you're familiar with the linear equation, and again, we know it's this equation because we're told it is a straight line. Y, of course, is the y value is equal to m, which is our slope. X is the x value, and then b is the y-intercept. So since m is our slope, whatever our slope value is going to be k because they are the same thing. So that is how we know that k is equal to 3.60 times 10 to the power of negative 2 liters over moles per second. So that is the entire answer for A. Everything that I have boxed in, and I hope that all made sense to everybody. So now for B, calculate the half-life for this reaction. So the half-life equation for the second order is T1 sub 1 half is equal to 1 over K initial concentration. So now it's just plugging in and solving for T. So we have T sub 1 half is equal to 1 over K, which we know is, I need to write smaller. We're running out of room. We have T 1 half is equal to 1 over K, we know is 3.6. I'm going to write it in E form just to save some space. Liters, moles, or actually I can write this in blue just to help people get a little bit of visual. I'm going to make this easy to understand. 3.6 e negative 2, which is the same thing as 10 times 10 to the power negative 2 liters over moles per second. Moles per second. Then times a initial, and we know what that is because the word problem told us. So then times 2.8 e negative 3. So we're going to plug this into our calculator. And I already did that for y'all. Go me, taking one for the team. And you can go ahead and double check my work. ChatGPT also double checked my work. But if you put it in correctly, you should get 9,920.6 seconds or somewhere around there. Professor Bayan always says within 5%. So that is now our answer for B. Now moving on to C. How much time is required for the concentration A to decrease to 7 times 10 to the power of negative 4 molarity? So now we are going to go back to our integrated rate law equation from A, and we are going to plug in our numbers and solve for T. So that's going to look like this, and I'm going to do this in purple. So our rate law or integrated rate law was 1 over A sub T is equal to K T plus 1 over A initial or A naught. So we know, so since AT is the concentration after a certain amount of time, the question gives us what AT was going to be. So we have 1 over 7.0, or I'm going to do 7 e to the negative 4 is equal to K, which we know is 3.6 e to the negative 2. T, which is what we're solving for. So let me go ahead and put that in a different color. T plus 1 over A initial, which was given in the original work problem, which is 2.8 e negative 3. So now we're going to solve for T. Hopefully you can do basic algebra. We're going to do minus 1 over 2.8 e negative 3 on both sides. Really should have zoomed in for this, whatever. Negative 2.8 e negative 3. And subtracting those two numbers, you get 1070.4. is equal to 3.6 e negative 2 t. Now we're going to divide by 3.6 e negative 2 divided by 3.6 e negative 2. So now we get t is equal to, and you should have gotten 29,761 seconds. That is our answer for C. I'm going to go ahead and take all of this and move that over here. Kind of, oh, I missed some things, but roughly moving that over there so it's out of our way. Hopefully you got all that. Feel free to pause the video. So now for our final question, question 79. It says one mechanism for the, if you can't tell I have dyslexia, it's really showing right now. Becomes really prominent when I'm tired. Let's try that again. One mechanism for the destruction of the ozone in the upper atmosphere is this given. Is this overall reaction? We're asked three questions. And let's start with the first one, which is A, which species is the catalyst? To answer this one, you need to understand that the catalyst is the species or something that is used in an early step of the mechanism and is then recreated again in a later step. So we need to look for what is used in the early steps. And we're given two things. We're given O3 and NO. So now we need to see which of those is then created in a later step. So now you need to look at step 2. I'm going to label these. Step 1. Let's make that skinnier. Step 1, and this is step 2. So now when you look at the products of step 2, and there is no NO3. There is no O3. We're given O2, but that is not O3. So O3 is not the catalyst. But we are given, or we do recreate NO as a gas. So that is why NO, oh, not NO2, NO gas is our catalyst species. Now for B, which species is an intermediate? An intermediate is a element or compound that is created, or I don't want to say created because it's a whole thing in science, but quote unquote created in an earlier step and then is used back up in a later step, but then does not show up in the final or in the summary of in the overall reaction. So to find this, we look at the products of step 1 and the reactants of step 2. So here in the products of step 1, we have NO2, and we have NO2 here again in step 2. And in step 1, we are also given for the products O2. So now we need, but we're not given O2 in the reactants of step 2, but we need to look even further just to make sure. We need to look at our overall reaction. O2 is one of the products in the overall reaction. So it can't be an intermediate because it exists in the overall reaction. It exists in the final form. So it's not an intermediate. NO2, though, does not exist in the overall reaction. So NO2 is our intermediate species. Give me 1 second. My dog wants in my room. Okay, now moving on to question C. Energy activation for the uncatalyzed reaction is 14 kilojoules. Energy active active activation for the same reaction when catalyzed is 11.9 kilojoules. What is the ratio of the rate constant for the catalyzed reaction to that for the uncatalyzed reaction at 25 degrees Celsius? Assume that the frequency factor A is the same for each reaction. So, since we're solving for the value of K for the rate constant, we're going to be using the Arrhenius equation from question 13, which is K is equal to AE to the power of negative A sub E over RT. Now that we have that, let's go ahead and list out all the numbers that we were given in the word problem. We're given uncatalyzed, I'm going to color code this purple. Uncatalyzed reaction is 14. For the uncatalyzed, we have EA is equal to 14 kilojoules. And then the temperature is the same for both of them. Hello? Temperature is the same for both of them. And the frequency factor is the same. So I will explain what that does later when we go through more of the equation. So temperature T is going to equal 25 degrees Celsius. And then we have our R, that's our gas law constant. We're going to use the 8.314 joules per mole Kelvin. Since we're using this one, we need to make sure our units match up. So we're going to turn this and we're going to turn the 14 kilojoules into joules by timesing by 1,000. There's 1,000 joules per kilojoule. That gives us 14,000 joules. And then we're going to add 273 to our Celsius to give us 200. Let's redo that. Give us 298 Kelvin. Now we're going to analyze this for our catalyst reaction, or catalyzed. Our energy activation is 11.9 kilojoules. Our temperature is going to be 25 degrees Celsius, and our R is going to be 8.314 joules per mole Kelvin. So same thing here, times by 1,000. And we get 11,900 joules, and then plus 273, we get 298 Kelvin. Okay, so now that we have all the information we need, let me go ahead and talk about how we're going to set up our equation. There's two ways to solve this. You can either solve the K value for the uncatalyzed and then solve for the K value of the catalyzed one and then divide those two numbers, or you can do it all in one foul swoop. I will show you what both look like. I'm not going to solve both, but I'm going to show you them just because everybody here has different levels of understanding of math. So for more math savvy people, doing it all together might make a little bit more sense or might be easier. Um, but before I jump right into that, I'm going to explain the ratio part. Every single ratio is a fraction. And when translating the words into the actual fraction, we look for that special word 2. The word in front of 2 is going to be the number on top of the fraction line, also known as the numerator. So catalyzed is in front of our word 2. So the catalyzed number will go on top. And uncatalyzed is after the word two. So it's going to go underneath the fraction line, also known as the denominator. So that's going to be our fraction. It's also really important to note that frequency factor A is the same for each reaction. And since we're dividing the two, the A will just cancel out. So the formula we're actually working with is going to be K is equal to e to the power of negative EA over RT. So now let me show you the two different ways that you can solve this. You can do because now we're working with K catalyzed over K uncatalyzed. That's going to look like this. I did not go to eraser. E to the power negative EA over RT. Let me color code just a little bit. Going to be green for the catalyst, green. E to the power of negative E sub A over RT over, this is purple, E, E to the power of negative E sub A R T. So what exponents rules tell us is that when you are dividing a number that has, when you're when you have a complex fraction like this, and you have an exponent over an exponents divided by exponents, and they have the same base, meaning that this number is the same, the exponents subtract. So this also equals e to the power of negative e sub a over RT minus minus negative e sub a over RT. As one way you can solve it. That is not the way I'm going to be solving it today in this video, but if this makes more sense to you, then go for it. I'm going to solve them individually and then divide at the end instead of dividing at the beginning. So I'm going to go ahead and do that now. But at the end, we should all get the same answer. So let's first solve for the numerator, which is going to be K catalyzed. So we're going to do K is equal to e to the power of negative e sub a, which in this case is going to be 11,900 joules divided by R, which is 8.3144 joules per mole Kelvin times 298 Kelvin. And you plug this into awesome calculators and you get K catalyzed is equal to, I've already done the math, it's you 8.24 e to the negative 3. And then, so now we have our K sub cat. We're going to solve for K sub uncat. So for the uncatalyzed one, of that purple, we have e to the power of negative 14,000 joules over R, which is 8.314 joules per mole Kelvin times 900, 280, oh my goodness, times 298 Kelvin words were on my side. So that gives you, plug that into your calculator. Oh, I'm sorry. Nope, not E. That gives you 3.51 E negative 3. And when I say E in this case, I'm not talking about the little e. I'm talking about the big E that symbolizes 10 times that exponent, in this case, negative 3. So now we go back to our original fraction we were looking at and we plug those numbers in. So we're going to do, so for K, for the ratio that we're solving for, K cat catalyzed over K uncatalyzed, that is equal to 8.24 E negative 3 over 3.51 E negative 3. So our answer will be 2.35. That is the answer to part C of question 79. Thank you for watching my video, and I hope this helped study for your test one.